Okay guys, so today we're starting our new unit. Our new unit is going to be on stoichiometry in the mole. So for today's lesson, we're going to need this page in our notebook, which should be page 1. We're going to be doing a lot of math, so it'll make our lives a lot easier if we have some sort of calculator. And then for a couple problems, we're probably going to want our periodic table. If you don't have this, you can still follow along and be fine. But if you do have one, it'll probably be a little helpful. Okay, so here's the concept of stoichiometry. So our last unit, we were working with chemical reactions, and we spent a lot of time figuring out how to balance our chemical reactions. So here I've got a balanced synthesis reaction where I'm told that I need 3 calcium atoms reacting with 1 nitrogen molecule to make 1 molecule of Ca3N2 calcium nitride. Now, atoms and molecules are so small, I can't go into a lab and count out 3 calcium atoms. I can't count out 1 nitrogen molecule. So how am I going to measure these out in proper relationships, in proper proportions, so that I can make this reaction run to completion, where I'm not wasting stuff or I don't run out, okay? That's the concept of stoichiometry, and it's one of the most useful skills that I'm going to have as a chemist, okay? Now, when I'm talking about stoichiometry, I'm going to have this word that I'm gonna see a lot called a mole, okay? Now, a mole is a really abstract concept, but think of it exactly the same way you would if I said a dozen. Every time I say the word dozen, I'm telling you that I have the number 12. I have a dozen eggs. I have 12 eggs. I have a dozen donuts. I have 12 donuts. Well, every time I say the word mole, I've got 6.02 times 10 to the 23rd. And for moles, I'm going to be counting atoms, okay? So if I said I had a dozen muffins, I have 12 muffins. If I said I had 1 mole of muffins, I've got 6.02 times 10 to the 23rd muffins. That number doesn't change. A dozen's always 12, a mole is always 6.02 times 10 to the 23rd. Okay? So if I have 6.02 times 10 to the 23rd marbles, I've got 1 mole of marbles. 1 mole of marbles is equal to 6.02 times 10 to the 23rd. Okay? So if I've got 12 times 10 to the 23rd marbles, how many moles would that be? Well, if 1 is 6, 12 would be 2 moles of marbles. Okay? If I had 18 times 10 to the 23rd, that would be 3. 24 times 10 to the 23rd would be 4. 30 times 10 to the 23rd would be 5, okay? So each time I increase my number of moles, I increase it by 6 times 10 to the 23rd, okay? So if I have 1 mole of carbon atoms, I've got 6.02 times 10 to the 23rd carbon atoms. Every time you see 1 mole, that number stays the same, okay? Now here's where it gets kind of confusing. Sometimes you'll see the word atoms, sometimes you'll see the word molecules, okay? So just like in my example, an atom is when I have an individual element by himself, just one. A molecule is where I've got 2 or more atoms. Okay? Now these can be tricky. Sometimes a molecule can be 2 identical atoms. So in my example, N2 is a molecule. I've got 2 atoms of nitrogen. Okay? It could also be composed of hundreds of atoms, and they could be different. Now this was also a molecule. I've got 3 CAs bonded to 2 Ns to make 1 molecule. Okay, so this is a molecule because it's more than 1 atom. This is a molecule because it's more than 1 atom. This is just an atom because it's by itself. Okay, so when I've got a molecule that's composed of 2 identical atoms, okay, so for example, N2, I've got a nitrogen bonded to an identical nitrogen. We call that a diatomic molecule. One of the most common ones that we're going to deal with is oxygen. Oxygen is never by himself, he's always O2. Oxygen is an element, I'm breathing in O2. So because oxygen is always O2, he is a diatomic molecule. Okay? Now when we talk about this, I can use Avogadro's number, the mole, 6.02, to count my atoms. I can also use it to count molecules. Okay? So if I was looking at this, if I've got 1 dozen oxygen molecules, 1 dozen oxygen molecules would be 12 oxygen molecules. Okay? And then it says each of which is composed of 2 oxygen atoms. Okay? So if each one of these molecules has 2 atoms, I would have a total of 24 atoms of oxygen in 12 molecules of oxygen. Okay? If I have 1 mole of oxygen, then I have 6.02 times 10 to the 23rd molecules of oxygen. If I know that each molecule of oxygen has 2 atoms of oxygen, 6 times 2 is 12, so I would have 12.04 times 10 to the 23rd atoms of oxygen. Okay? So a dozen is always 12, a mole is always 6.02 times 10 to the 23rd. Okay? So we use a mole to count our atoms because I can't actually physically count them out. The problem is that even though this gives me a starting point, it doesn't give me the end point yet. And here's why. There is no measuring tool that will count out moles. I can't stick anything on a scale or a beaker or a balance or any kind of measuring tool and have it measure moles. So what we talk about is something called molar mass. Okay? The molar mass is how much 1 mole weighs. Okay? Now here's the problem. A mole is always the same number. If I have 1 mole of oxygen, it's 6.02 times 10 to the 23rd. If I have 1 mole of hydrogen, 6.02 times 10 to the 23rd. If I have 1 mole of helium, 6.02 times 10 to the 23rd. But think about it like something that is a little easier to visualize. Let's say I have a dozen baseballs, 12 baseballs. I've got a dozen bowling balls, 12 bowling balls. Same number of baseballs as bowling balls. Do they weigh the same? No. My bowling balls are going to weigh way more. Same thing with my atoms. If I look at my periodic table, a hydrogen atom is really light. He only weighs 1. If I look at calcium, he's way heavier. He weighs like 40. If I go all the way down here to lead, lead's like a bowling ball. He weighs 207. So before, when we looked at these numbers on the bottom, we talked about the atomic mass. Now we're going to talk about them as molar mass. It's still how much it weighs, but it's how much 1 mole weighs. When we talked about atomic mass, we measured it in AMU, atomic mass units. When we're talking about moles, we're going to weigh things in grams. Okay? So 1 mole of hydrogen is 6.02 times 10 to the 23rd atoms. If I had 1 mole of calcium, still 1 mole equals 6.02 times 10 to the 23rd atoms. Okay? But these 6.02 times 10 to the 23rd atoms of hydrogen only weigh 1 gram. The 6.02 times 10 to the 23rd atoms of calcium, they're gonna weigh 40 grams. My calcium is way bigger than the hydrogen atoms. Because they're bigger, they weigh more. Same number of moles, same number of atoms, but they have different molar masses because the atoms have different sizes. Okay? So that's what we're looking at in this section here. They tell me that the molar mass of oxygen is 16 grams. If I look at my periodic table, the molar mass of oxygen is 15.999, so 16 grams. Okay? So because I have 1 mole, how many atoms is that? 1 mole is always 6.02 times 10 to the 23rd. Okay? That doesn't change. Now here's where it gets a little trickier. We said oxygen was diatomic. He always needs a buddy. So I never write oxygen as O. I always write him as O2. 1 oxygen weighed 16 grams. 2 oxygen weighs 32 grams. Okay, so 1 O is 16, 2 O's is 32. Okay, still how much 1 mole weighs. Now, when I talked about atoms, it was just 1 O. Now I'm talking about molecules. Okay, so if I have 1 mole of O2, I still have 6.02 times 10 to the 23rd oxygen molecules. Now I know that in each molecule, I've got 2 oxygen atoms. So even though I've got 6.02 times 10 to the 23rd molecules, I would have 12.04 times 10 to the 23rd atoms of O. I need twice as many O's to make O2. Okay, so here's kind of how that works. 1 dozen eggs weighs 1 pound. So if I've got 1 dozen eggs, it weighs 1 pound. If I've got 3 dozen eggs, how many pounds would that weigh? Hopefully everybody said 3. 1 dozen is 1, 3 dozen is 3. I just multiplied that by 3. Okay, so if I say 1 mole of oxygen weighs 32 grams, then 3 moles of oxygen would weigh how many grams? Hopefully, I would just take this number, just like I did here, times 3. I would say, oh, well, that weighs 96 grams. Okay? So when we have a compound, we need to find the molar mass of everything that makes up the compound. Okay? So here I've got H2SO4. H2SO4 is made of H, S, and O. H, and I'm going to round this, weighs 1 gram. But because it's H2, I've got 2 of those, so I multiply. S weighs 32 grams. No number, so there's only 1. So I've got 32 grams worth of S. O was 15.999. We round him to 16. SO4, I've got 4 O's. 16 times 4 is 64. 2 plus 32 is 34. Plus 64 is 98. That's where that number came from there. Okay? If I add up the molar mass of all of the parts, I get the molar mass of the whole. Okay? So for elements, I just look at the periodic table. For compounds, I have to find all of the elements on the periodic table and add them up to get my total. Okay? So here, it tells me that I've got 2.5 moles of H2SO4. I know that each mole is 6.02 times 10 to the 23rd molecules. Oops, pretend I spelled that right. So if I wanted to find out how many molecules I had in that many moles, I just multiply. 2.5 times 6.02 times 10 to the 23rd, I should get 15.05 times 10 to the 23rd. Okay? Now, if you've got a scientific calculator and you put this in just like this, your calculator probably would have said 1.505 times 10 to the 24th, exact same thing, okay? If you have a calculator that you don't want to deal with scientific notation, I just multiplied those two numbers, 2.5 times 6.02, and got that number. And then I know it needs to be multiplied by 10 to the 23rd. Works out the exact same way, okay? So the last one is a little trickier. How do you think you'd solve the last one? If I've got 15 times 10 to the 23rd molecules, how many moles would that be? Hopefully, you said that I know that 6.02 times 10 to the 23rd molecules is equal to 1 mole. So if I divide those two numbers, I don't want to deal with scientific notation, so I'm going to say 10 to the 23rd divided by 10 to the 23rd. Those cancel out. So I would have 15 divided by 6.02. I should have about 2.18 moles. Okay. Now we went through this pretty quick. We're going to practice with this a lot because this is one of our most helpful tools. So I want you to take a second and try to do some of the problems on page 2. Okay. Work down to this point, and then we'll talk about it.